Let's explore signed number representation in digital logic and design. We will discuss the primary methods for representing signed integers in binary systems. This is an important topic when dealing with negative numbers in digital systems. One way to represent signed numbers is the sign magnitude representation. Here, the most significant bit, or MSB, represents the sign of the number. The remaining bits represent the magnitude, or absolute value of the number. If the sign bit is 0, the number is positive. If the sign bit is 1, the number is negative. Therefore, in the representation shown, S is the sign bit, and the X's are the magnitude bits. Here are a few examples of the sign magnitude representation using 8 bits. For the positive number, the binary representation is 0, followed by 0001101. The sign bit is 0, indicating a positive number, and the magnitude bits represent the decimal value 13. Therefore, the decimal value is positive 13. For the negative number, the binary representation is 1, followed by 0001101. The sign bit is 1, indicating a negative number, and the magnitude bits represent the decimal value 13. Therefore, the decimal value is negative 13. Another way to represent signed numbers is the 1's complement representation. To represent a negative number in 1's complement, you simply invert all the bits of the positive number. That is, change all the zeros to 1's and all the 1's to zeros. Mathematically, the 1's complement of X is equivalent to the bitwise not of X. Let's look at a couple of examples of 1's complement representation, again using 8 bits. To convert positive 13 to negative 13, we start with the binary representation of positive 13, which is 0001101. Then we invert all of the bits. All zeros become 1's and all 1's become zeros, resulting in 11110010. This is the 1's complement representation of negative 13. Similarly, to convert positive 5 to negative 5, we start with the binary representation of positive 5, which is 000000101. Then we invert all of the bits, resulting in 11111010. This is the 1's complement representation of negative 5. Another important method to represent signed numbers is the 2's complement representation. To represent a negative number in 2's complement, you first find the 1's complement of the corresponding positive number, and then add 1 to it. Mathematically, the 2's complement is equal to bitwise not of X plus 1. Here are some examples of 2's complement representation. To convert positive 13 to negative 13, we start with the binary representation of positive 13, which is 0001101. Then we find the 1's complement by inverting all the bits, which gives us 11110010. Finally, we add 1 to the 1's complement, resulting in 11110011. This is the 2's complement representation of negative 13. For the second example, to convert positive 5 to negative 5, we start with the binary representation of positive 5, which is 000000101. The 1's complement is 11111010. Adding 1 to it gives us 11111011, which is the 2's complement representation of negative 5. Let's briefly compare the 3 methods we discussed: sign magnitude, 1's complement, and 2's complement. In sign magnitude, the most significant bit represents the sign, and it has 2 representations for 0, positive 0, and negative 0. In 1's complement, you invert all the bits to get the negative representation, and it also has 2 representations for 0. In 2's complement, you find the 1's complement and add 1 to it. This method has only 1 representation for 0, which makes it the most widely used method in modern computers. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.